Our next speaker, well, here's his title, sTeX, a LaTeX-based ecosystem for semantic and active mathematical documents. Dennis Müller and Michael Kohlhauser, they're from the Universität of Erlangen-Nuremberg, a place I know quite well. I was there for I visited a couple of times back in, what was it, the 1980s, mid-1980s. So I think that predates this particular, these particular authors. So please, Michael can't be with us, but Dennis is going to be the speaker. He was a PhD student with Michael, and take it away, Dennis.
Thank you. Can you hear me all right?
Yep, that sounds fine. You sound good.
One slight correction, I already have my PhD, but thank you and good morning. I'm here to present to you sTeX, a ecosystem at the core of which is the sTeX package for LaTeX. sTeX itself is not new. It's Michael Kohlhaaser's brainchild, my mentor and co-author. I think it was first published in 2008. But over time, more and more serious problems crept into the whole project. So at some point, about a year ago or a year and a half, I managed to convince Michael that we basically need to scrap the whole code base and redesign, reconceptualize, and ultimately re-implement the whole thing from scratch. The result is now sTeX3. We deliberately decided to skip a version number up to 3 immediately because we implemented it in LaTeX 3. And the other reason being that the changes are significant enough to warrant that. Also, as we now noticed, since sTeX is very much influenced by semantic web technologies, which used to be called Web 3.0 before the cryptocurrency communities got their hands on that term, that also fits nicely. So some background. I'm not the first person at this conference to emphasize the importance of using 21st century technology when it comes to documents, in particular HTML and other dynamic document representation formats. But I should mention, or rather emphasize, that this is especially relevant when it comes to LaTeX, when it comes to mathematics. Because in mathematics, LaTeX is for all practical purposes the game in town when it comes to representing documents. Not just that like tech syntax or tech-like syntax is basically ubiquitous everywhere where you want to like typeset formulae in the first place, but also basically the whole scientific publishing industry in mathematics and related disciplines is based on LaTeX. To the point where I'm pretty sure that if you want to publish any paper and you're not prepared to submit LaTeX files that can be compiled with PDF LaTeX, you might have a very hard time. Having said that, if you keep in mind that ultimately the whole point of any kind of document is to basically transfer the semantics of what's written in the document from the brain of the author to the brains of the readers, then mathematics has a very peculiar property which makes this especially relevant when it comes to not only being concerned with layouting the exact typesetting of things, which is the whole area of formal mathematics. I'm assuming that most of you don't really know what that is. The core idea is that for mathematics, we know how to represent the precise semantics of mathematical statements in such a way that computers can act on it, which in the ultimate variant of that enables things like fully computer verified math and automated theorem proving and interactive theorem proving. The ideas behind that go back to basically the early days of modern formal logic. And if you keep that in mind, what we can do if we represent mathematics formally, i.e. semantically, machine actionable, you might wonder why we don't just write all math that way in the first place? And the answer is, unfortunately, that doing that is extremely difficult. My favorite example is the most famous case of a mathematical theorem being fully computer verified, which was Thomas Hale's proof of the Kepler conjecture. He published his informal proof, like written as a PDF, so classical way, sometime in the 90s, and then announced that he's going to fully formalize it and computer verify it. And that endeavor took 16 years, was published in a paper with 22 authors, all of whom are experts in formal systems, and is estimated to have taken around 30 person-years in total. One of the reasons for that is, or one of the additional problems with all of that is that formal mathematics is extremely counterintuitive for informal mathematicians. Just as an example, the lean is one of those theorem provers, and I think it's safe to say that it's probably one of the best, if not the best, currently existing theorem prover systems. And here's the introduction to theorem proving in lean. And what it does is it starts out by honest to God theory. You have to explain to people what is dependent type theory, what is simple type theory, how do dependent types works, what is the propositions as types paradigm, how do we use it? And then lots and lots of text just about ubiquitous concepts like universal quantifiers and literally equality. If this comes across as if I'm now trying to disparage lean, let me assure you I'm not. As mentioned, lean is probably the best system we currently have in that direction. And if you understand how these systems work, you understand why they do it that way. In fact, I would do it the exact same way, and I have done it the exact same way in the past. What I'm trying to get at here is that if you want to use formal systems, you have to think about mathematics in a completely different way than mathematicians usually think about math. Oh, I'm seeing a pop-up. By the way, if you have any questions during the course of this talk, feel free to ask them immediately. I just have no way of seeing the chat or anything, so you're at Ross's mercy, I guess. And one of the reasons why all of this is so difficult and takes a lot of time is that to formalize any kind of formal mathematical setting, you also need to formalize everything that transitively goes into that. So for example, if you wanted to formalize the Pythagorean theorem, so in a right triangle, a squared plus b squared equals c squared, you also have to formalize what is a triangle, what is an angle, what is a line, what are points. You have to implement arithmetics on angles. You have to formalize what numbers even are and all of that stuff. So point being, formal mathematics are difficult to learn. They're difficult to use. They require huge investments. Yeah. Having said all of that, here's one example in case you've never seen how these systems look like. So here's an honest to goodness real math theorem, right? In any right triangle with sides a, b, c, and right angle opposite to c, the equation a squared plus b squared equals c squared holds. I think you've all seen that. And here's what that looks like in theorem prover systems. And if you're a computer scientist or you have some programming experience, you might look at this and think, okay, this is just syntax, I can learn this. If you're a mathematician, this is scary. Also, something I really only noticed this morning, this is the most famous theorem about triangles in the history of mathematics. And the word triangle doesn't even appear anywhere here. I didn't even notice that before because like I've been sufficiently brainwashed by formal systems that it's obvious to me that why would it appear here? But yeah, if you're a mathematician, that would already be very strange. So having said all that, notably, a lot of these difficulties with formal mathematics disappear if we just relax the requirements a bit. If we don't insist that everything has to be fully formal and fully verifiable by a computer, and you still get a lot out of it if you just do things like only semantically annotate some words, for example, right? So here's a statement: a group is a structure such that if you just semantically annotate what you exactly mean by the word group here, or what you mean by the word structure here, with some unambiguous concept declared somewhere, you can already do a lot of funky stuff, which I'm going to show you later. Or if you just leave gaps in a formalization, right? So you could have an expression like this, and you could say, yeah, this is a tensor product applied to something which I don't know how to really formalize it, but in there, then there's this variable I. Again, we call all of these principles flexiformality, right? So you introduce some aspect of formal mathematics into the whole thing, but without like having to insist on everything being fully formal. And that way, of course, you sacrifice some things. So you can't do fully formal theorem proving anymore, but you can still do a lot of stuff. You can disambiguate concepts. You can do things like formula search. We have a search engine called MathWeb Search that only requires like the basic syntactic structure of a formula to be known, but it doesn't need to know what every single symbol in the thing means. Yeah, I'm going to show you what you can do later. I have 3 more technical slides, which I have to get through, and then I will actually just show you what you can do. So the goal of sTeX is to allow for integrating semantic annotations into arbitrary LaTeX documents in such a way that you can do anything from just writing plain old LaTeX with no semantic information whatsoever, up to indeed like fully formally annotating everything so that you get like all of the formal services out there that are in principle possible. This whole pipeline consists of 3 things. The first one is this, the sTeX package, which you can just include using use package in any plain old text document. With sTeX, you can declare semantic macros that represent mathematical concepts. And then these macros you can use to semantically annotate document fragments. Subsequently, you can use the RosTeX system to take these LaTeX sources and convert them to XHTML. And in the HTML, you will not just like preserve the document itself, like the document text, but also it will preserve all of the semantic annotations that you do in LaTeX. And then afterwards, the MMT system, another piece of software, can like import these HTML. It can extract all of the semantic annotations, construct the fully formal syntax trees, so you get a fully formal representation of whatever you typed in there, and then can serve the HTML and augment it with various services that act on the semantic annotations. Here's a link to all of the active documents we currently have, which I will show you later. That's something like 3,000 pages of course notes. Michael, being the insane person that he is, has literally written all of his lecture notes over the last, I don't know, 12 or 15 years in sTeX. We've built libraries with various mathematical concepts, by now more than 2,250. Also lots of computer science stuff. And we've now started, now that sTeX3 actually allows us to do that, started to also like write honest to goodness research papers in sTeX, which we then can actually submit to arXiv and Springer and EasyChair and all of these things. With some caveats, if you know how Springer actually works with respect to LaTeX, but yeah. So here's how sTeX roughly works. So in sTeX, you can declare symbols which represent a mathematical concept, and then associate that mathematical concept with a semantic macro, which you can then use to annotate stuff. For example, we can declare the natural numbers by just doing symdecl nut. Nut will then be the name of the semantic macro, and give it a proper name, just like name equals natural number. And now I have a macro named nat, which I can use for semantically annotating things. You can also associate notations with semantic macros for typesetting in the math environment. So if I do a notation like this here, then I can just in math mode type \nut and it will print this thing. As you notice, all of the slides I'm showing you here are written in sTeX, so everything that's like printed in this weird blue thing is actually a concept somewhere known to the sTeX system. And if you hover over it, it will show you like a unique identifier that is available. These symbols we can then collect in modules, which you start with such a begin S module. And then these modules you can just import from anywhere, analogously to LaTeX packages. The difference being that unlike LaTeX packages, modules don't just give you macros that are like used for typesetting, but they bundle various symbols and concepts, the semantic macros, the notations, and text fragments like the definitions, fundamental theorems, documentations, and so on and so forth. And that allows us to build whole libraries of these mathematical concepts, A, modularly, and B, importantly, collaboratively and communally. So if at any point you like want to use this thing and you realize, okay, I have no idea how to do this particular mathematical concept, you can basically leave it to others and then subsequently just import it without copy paste or whatever. That's in so far very important as I mentioned, formalizing stuff really fully formally can be very, very difficult. So it's nice to be able to just leave that to other people or just to the community as a whole. Right, so having sTeX documents, we want to convert them to HTML. And I'm very sad to have to say that I had to write my own system for that. Dejan Ginnev recently posted on Twitter where he counted the currently existing and actively being maintained software systems for converting LaTeX to HTML in 2022, and he found 10. I've toyed around with a lot of them. I can't say that I tried all of them, but I had a rather simple test. Given the source code for my doctoral thesis, what do these systems do with it? And the sad result is none of them produced any output whatsoever, or like died somewhere in between. So Tech4HT, for example, gave me a couple of pages and then it died. That's very sad. And I'm very unhappy about that. But yeah, as a result, I felt forced to basically write my own thing, which I did in Rust. And the idea that I had is what we need to do if this is going to work for arbitrary LaTeX documents, which I wanted it to do, is we have to make sure that such a conversion engine basically has to behave exactly as PDF LaTeX does. And that was my goal. So what I did in RustTech is that I only implemented the majority of like plain tech, eTech, PDF tech primitives, tried to map those to a CSS module, basically using flexboxes. And then the first thing that RustTech does if you try to convert any LaTeX document is that it processes a user's latex.ltx first. So it does assume that you have some LaTeX distribution installed, but let's be fair, if you use LaTeX, you probably do. Just to give you an example of what this looks like. This is my doctoral dissertation, which, as I mentioned, I tested out, and this is the HTML I get out with RustTech. You'll notice it looks conspicuously like a PDF, which hopefully makes sense if you think about how it works. There is, of course, some trouble. My MathML knowledge is by far not good enough that I could make things work ideally. In particular, you might notice some things like this. But in general, and to me, the important thing is it produces HTML. Everything that's in the text source is there somewhere. It just might look ugly. This, by the way, is the tcolorbox package. I think that's one of the things that tripped up most of these conversion engines. And as you can see, it also trips up mine, because what it does in the back end is that it uses PGF to produce the color box and then puts the text on top. And all of this is really horrible if you want to do it in HTML. But at least I get something out of it, which was unfortunately a necessary requirement. Having said that, given the way that RustTech works, it has no special treatment for sTeX itself either. All it provides is a method for attaching XML attributes to HTML nodes. That's the only thing that I really need. So I very specifically designed sTeX such that it's configurable. So if at any point other conversion engines allow me to do exactly that, i.e. attaching attribute annotations, I can use other systems as well. Or if anyone invents a whole new document format, unlike HTML, where you can like introduce annotations, you can use that too. In particular, I'm still very much hoping for LaTeX-ML, which reminds me, Peter Williams in his talk, How Does Time Work? I think the day before yesterday, mentioned that he's annoyed that he has troubles reading papers on his mobile phone. He also said that he works on archive, so I'm somewhat surprised he doesn't know this. If you go on archive.org and open any kind of paper and you replace the X by a 5, you get an HTML version of the exact same paper. And this is what LaTeX-ML does. It has like images, it has mathematical formulas, in case I can find one somewhere. Here's one, and they look really nice, a lot nicer than what I can do in sTeX. It even does have a dark mode. And in particular, I've also heard that by now LaTeX-ML has support for the Beamer package. It has support for XY, which is used for like doing commutative diagrams and things like that. And that in particular sounds like black magic to me. So if at any point I can actually use LaTeX-ML as well, that would be wonderful. And I'm just waiting for the day where that I can do that. Right, and finally the MMT system. So once we have HTML, we can import that HTML into MMT, which is a generic software system that basically tries to do everything that these formal systems like theorem prover systems do, but on an abstract level, so that you can basically instantiate it with different ideas of what the system should do, up to and including type checking and type inference and all of these fancy things. Most of this is not too important. It uses OmDoc or OpenMath as a backend language. That's a document representation format that Michael Kohlhase, my co-author, invented. Sorry, is there a question? Or was that just background noise? Okay. And ultimately, MMT already integrates sTeX, so you don't have to like bother with two systems. And by now, we've also bundled the MMT system into a VS Code plugin so that you get a proper IDE that you can work with, and which makes the whole setup as painless as humanly possible, I hope. And having said all of that, I will actually spend the rest of my time showing you what this actually looks like. So here we have the VS Code IDE. So this is just a standard LaTeX document. We do use package sTeX, and then we can open a module. And here on the right side, you can see the PDF, but I try to make everything as big as possible so that it's actually legible over Zoom. And yeah. So we can declare a new concept, nat for natural numbers, which immediately generates a semantic macro. We can give it a name. And now if I do a sim name nat is, it will produce this here. And as you can see, this is the PDF. It will show you a URI. Or you can annotate arbitrary text. So you can do a symref nat and then write positive integer, and then it will associate the text positive integer with that concept. Or various syntactic variations that you can use. You can give it a notation. So here we give nat a notation, mathbbn, and we also can give that notation an identifier. So we can then use square brackets to explicitly tell us which notation we want to use. And as you can see, that produces mathbbn, and it's highlighted in blue because that's the way I do it in this document. But all of this highlighting functionality you can fully customize, of course. You can add more annotations. So if you want to write the positive integers as actually mathbbz with a plus, you can do that as well. And of course, you can just use the semantic macro without any optional arguments, and it will just use the first notation that was provided. Semantic macros can also take arguments, of course, that's important. So if you want to do something like addition, you can just tell it to explicitly take 2 arguments and then give it a notation. And now if you write nat plus and give it 2 arguments, it will actually like print a plus b here, and the plus is now highlighted. You can also invoke the notation itself without giving any arguments, provided you tell it how to do that. That allows you to write \nat plus exclamation mark, and then it will just print the symbol plus. We have similar functionality to mark up whole statements. So, for example, we could declare commutativity. What does it mean for something to be commutative? Commutative is a property of an operation, so it takes 1 argument, namely the operation. And then we can write down the definition, and we can fully semantically annotate if we want to go overboard the whole statement, which in the PDF looks like this then. Oh, addition. Sorry, here it is. A binary operation, blah, 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 is called commutative if the equation holds for all things. And if you annotate all of this fully semantically, the MMT system in the background will actually know the precise formal definition of what you wrote down here. Then you can state theorems about it. That works exactly the same way. And what MMT then can do, except for like processing all of this stuff and serving it as an HTML, which I can do by just quickly compiling the document. Ta-da! Here's the HTML version. And now you can notice what you get out of it. So I can still hover over all of these things. And now MMT does some fancy magic. For example, here where I have provided commutativity with an actual definition, if I now hover over commutative, it will show me this definition right here in the document, which is extremely helpful if you keep in mind how complicated mathematical documents can get. And in particular, if you really go overboard and fully formally annotate anything, MMT can even type check this. So if I introduce a variable, which you do with this syntax var_def here, and I give it a nonsensical type. So I'm now saying, well, the variable b is a foo, whatever that means. MMT doesn't know what a foo is. And if I now write nat plus a and this variable, the MMT system in the background will check, okay, natural plus has type. It will show you if you hover over it, I guess. Where is plus? There it is. Right. It knows that the type of this function is it takes 2 natural numbers and it turns in natural numbers. So it recursively knows that if I write, nat plus a var b, a will have to be a natural number and var b will also have to be a natural number. And then it tries to do that. And when it tries to do that, it will tell me, no, invalid unit, blah, 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 blah. Here's the whole proof tree of it trying to prove that this thing actually has a well-defined type. And at some point, it will fail because it now has to try to prove that foo is the same thing as the concept of a natural number, and then it will complain. So this is very helpful for catching just things like typing errors early, ideally. I should mention that this IDE is obviously very much a work in progress, so this squiggly yellow line should be here. Unfortunately, it's not. One more thing we can do in the IDE, as I mentioned, we can develop whole libraries of this stuff communally. We have a lot of those libraries, so this one is one that I have actually like locally available. These ones I do not. They're available on our GitLab instance on gl.mathhub.info. But I can now just download it right in here. I can also search for content. As I mentioned, the whole thing is very brittle, so I'm hoping this will now work. If it works, yes, it does. So it will both search my locally available modules and the ones on mathhub.info to see what it can find. If I search for abelian, I can also search explicitly for definitions or for theorems or for examples. And then again, I can just immediately download it, import the modules that are in there using this import module syntax. And then I can work with those. For the whole thing to work, of course, you have to like somehow tell sTeX where it can even find all of these modules that I'm referencing. We have a particular directory structure for how that works. So the IDE already knows where these are to be found. So all of those are in particular directories in one folder somewhere on your hard drive. And all you need to do is tell the system where to find that folder. You can either do that with a package option. So I can do mathhub equals and then put a file path here. Or you can define a macro, def mathhub, and then put the file path here. Or the most versatile and useful way to do it is to declare an environment variable, because the nice thing is in LaTeX, as I found out by Googling heavily, you can actually call kpsewich without having to use the shell escape command line option. And that allows you to actually read environment variables within LaTeX. So that is very nice. And of course, then you set the environment variable once, and then you never have to bother about the whole thing anymore. Here is what the MMT server or the MMT system does with this document that I've shown you earlier. So after you convert it to HTML, MMT will just extract all of the declarations and then show you all of the information. Right, so it now knows natural number, it knows addition, it knows that I've included a module for using functions, and it can even do type inference. So when I wrote somewhere where defined commutativity as, okay, it takes an operation and returns the proposition for all A, for all B, A circle B equals B circle A. It has also inferred the type and has realized, oh yeah, this is an operation that takes an operation and returns a proposition. If you use modules and you properly structure them, you also get these neat little module graphs in here. In case you ever want to see that, this is the whole graph of all sTeX modules we currently have. It has 6,577 nodes. It really brings JavaScript and my browser engine to the breaking point. So I can show you a more compact one. For example, here's everything we have in the algebra library that we currently have. And then you really get this nice picture of how all of these different concepts relate. So a group goes into trivial group and goes into subgroup, and subgroup goes into normalizer and centralizer. Also, subgroup uses the concept of function restriction. And yeah. And one more nice thing you can do if you know about all of these concepts is you can generate guided tours. Here's one nice example. This is just one slide somewhere from Michael's lecture notes. So you might look at this and think, okay, systematic search procedures. Okay, here it says what systematic means, but okay, what does it mean for a systematic search procedure to be complete? That is a typo, complete. So you can now hover over this and it will tell you, and then you can hover over solution and then it will tell you. But going that way at some point will just get really tedious if you have to like step top down. So instead, you can do this guided tour button, and now it will just take the dependency graph of modules associated with that concept and linearly order them. And now it starts with 0. It tells you what equality is, and then gives you these kind of mini course of all the definitions that you need to ultimately understand what it means for a strategy to be complete. Because sTeX has a special mechanism for being multilingual, so you can like inherit formal concepts between modules that contain the same content basically, but in different languages. I can also do lang equals de, and now I will get the exact same course, but everything replaced by the German variants. We mostly have content in English, of course, and a lot of German. Other languages, we have some, but very little, in fact. Yeah. And finally, one more thing I want to draw your attention to. Actually this month, a paper has been published on the changing notion of proofs between generations by a whole host of authors. It's a very nice paper. It's highly readable. I recommend it to everyone. And you will notice that one of the authors here is Leslie Lamport. So the guy who literally put the lay in LaTeX. And he has one section in this paper where he not just makes my argument for me when it comes to like why formal mathematics is important and why we should care about it, right? So there is evidence that about 1/3 of all published refereed math papers contain significant errors, and then goes on to like argue for formal methods. But in particular, one thing I didn't know is that Leslie Lamport apparently for decades has been arguing for mathematicians to use structured proofs, where structured proofs are this way of structuring a proof by basically representing it as a nested list of individual proof steps. And if you do it, you get a much better overview of how the proof as a whole actually proceeds. And then he says, and this I want to quote in full, making a proof more rigorous requires filling in all the gaps that could conceal errors. This means making it longer. Making a prose proof longer makes it harder to read. But with hierarchical structure, the extra length makes the proof easier to read. The additional explanation appears at lower levels of the hierarchy, so it doesn't obscure the structure of the proof. This will be especially true when mathematicians stop producing pictures of print on dead trees and start using hypertext. So lower levels of the proof can be hidden when not being read. So here, take it from the father of LaTeX himself, and I couldn't agree more. So of course, sTeX supports structured proofs. It actually has supported structured proofs for decades, but now that we actually can generate HTML from it, we actually get exactly what Leslie Lamport wanted. So here's a proof. We can mark assumptions, we can mark subproofs, we can mark individual proof steps. This is what the PDF looks like. And you will notice that all of this text in this first subproof doesn't even appear over here. That's because I've hidden it. But if I now convert it to HTML, there it is. And now I still get the same layout as before, but now I can actually like collapse this and expand the individual proof steps. And if I like just collapse all of them, then I really get a really nice overview of how the proof as a whole actually proceeds. Yeah. Finally, of course, the slides that I used for this talk also exist as HTML. All of our content is on mmt.beta.volki.quark.info. The URL is not very nice yet, but you can look it up in the paper, which we submitted and is linked in the program for the conference. Again, this is now HTML, so you can hover over everything and it will tell you exactly what's going on. Yeah, we also have by now 3 research papers written in and on sTeX, including this one if you really want to get into the nitty-gritty details of how you can like do more complicated formal representation of things. Yeah, and finally, some future work. What we currently can't do, but which should be easy to do, is if you have an HTML representation and the server that hosts the HTML knows all of the concepts and knows all of the different notations that are out there, then a reader can, in principle, just pick whatever notation he prefers. If you know about mathematics, you know that there are lots of different conventions when it comes to notations. And picking the one that you're familiar with makes reading a document a lot easier. We're also actively working on user models where we want to have a probabilistic model that represents what we think a user already knows. That makes it much more effective to generate proper guided tours specifically tailored for users. For example, by just omitting everything that we know they know already anyway, or by recommending them appropriate examples based on what prior knowledge they have, by showing them code examples in whatever programming language they know, which is very helpful at a computer science department. And ultimately, of course, the holy grail would be to fully integrate sTeX with existing software for mathematics, such as computer algebra systems and theorem provers. This will require quite a lot of research, but it's not as far out there as you might think. Basically, my PhD thesis was about how we can do these kinds of integration things in general. And now we basically just have to do that properly and with sTeX. Yeah, and that brings me to my end. Yeah, So here's one final theory graph from the area of formal logic, which is nice to look at. Yeah. Thank you very much.
Well, thank you, Dennis. Thank you for an absolutely wonderful talk and some fabulous work that you've done there. I noticed that the two most relevant guys for LaTeX ML are in the audience, and so I've already opened them up to be able to speak or answer any questions if they want to. They're free to speak. And someone else, and David Carlisle, of course, I'll allow David Carlisle to speak. So yeah, go ahead, guys. David, Bruce, Dayan, whatever.
I'll defer to Dane and Bruce first.
Well,
If
they
I-
haven't
if they
actually.
want.
They haven't actually said that they wanted to speak.
Oh,
but
sorry.
I-
Okay, I'll ask in that case. So I'm David Carlisle. Yeah, thanks for the talk. So, as you may know, the MathML 4 is currently in sort of initial phases, and we have a kind of a similar system for annotating presentation MathML with content.
Mhm.
Not that surprising, it's similar given some shared personnel in the history of these things. But one of the big missing parts of that is generating those annotations. So basically, you can annotate with an XML attribute, the semantic hint for the presentation, and generating that from tech would be a requirement in practice to get it. So if at some point we should chat to you, or of course you're both welcome to be on the working group.
Yeah, isn't Michael on the working group already?
No, he was. He's not. He never rejoined when we reformed to do MathML 4.
Okay.
You could give him a nudge if you wanted to.
I will gladly do that. Yes.
But Dayan is and Bruce are. So yeah. But generating this from tech. As you'll know, from an arbitrary traditional LaTeX document, inferring the semantic structure is a bit of a
yeah.
But from your input, it should be doable. It's just a matter of. It's a bit harder at the moment because we haven't actually finalised the syntax you're aiming for, but that's work in progress. But yes, I just
also, and now that you mention it, I think one of the other problems with like content MathML is that there's no shared ontology about like how to actually precisely specify the semantics of the thing, right? As far as I know, they're just arbitrary identifiers, but there's no like universally agreed upon library. So if
we in MathML 3 we explicitly reference every content MathML to an open math content dictionary.
Okay.
With you should ask Michael about that. He wrote most of that. Right?
Yeah.
So in this is similar. We have a big database of concepts that Dayan basically is accumulating, but the exact details of how it works are in flux. But it would be good to get this in alignment by the time we ship, which will be sometime next year probably.
Okay, I'm looking forward to that.
If you look at the MathML 4 draft, chapter 5 is where you want to look and skip the rest.
Okay. But while I have you here, I want to thank you very much for being as active on Stack Exchange as you are. You can
Any
imagine
problems, it's not my fault.
But you can imagine that when I was trying to write Rustic, I regularly run into problems of, okay, how the hell does this even work in Tech? What is happening here? And multiple times, I think at least 2 times, you were the first one to respond quickly and very informatively. So thank you very much for that.
I have used tech before, I must admit.
Yeah. So. I am very well aware.
Okay,
also, your 12 days of Christmas is one of the things that I tested Rostech on.
Yes, it's an important test, that one.
Yeah.
Okay, there's a question in the Q&A. Can you open that up and see it? Or do you want me to read it out?
I can't see it until I stop, but I don't think I need the screen sharing anymore.
Yeah. Okay, so is there a dependence or relation between formal math and ontologies with inferencing inside?
Dependence relation between formal math and ontologies. I'm guessing you mean between formal math on one side and ontologies on the other side. There's little inferencing that can be done because most ontologies are not sufficiently formal to allow that. But to some degree, it is possible to transfer actual expressions between annotated with ontologies and formal mathematics. We kind of toyed around that in the course of my dissertation. So, for example, things like writing down an expression in MMT surface syntax, translating it to Sage, have Sage do some computation on that, and then translate it back into MMT, which again is like actual formal math. So there's ways to do that, but to be honest, it's very cumbersome and requires a lot of work.
Oh, there's another
I hope
one.
that answers the question because I feel like I might have misunderstood it.
So Bruce Miller has made a comment. Okay, so nice talk. Okay, so
thank you very much.
Am I in here alive now? I did want to respond.
Yeah.
To Ross's
Yes,
invitation to comment. It's a nice talk. I really like that. Yeah, I mean, an obvious aside, we should be talking again.
Yeah, I'd be happy to.
I'm really impressed with what you got. LaTeX ML ought to be able to do all of that. A bit slower in the current version. I don't know if Dayan has any comments about a future faster version.
Okay, Dayan's made a comment in the chat. So it's 5 a.m. for him, so maybe we'll leave that out. Okay. For just one comment in closing, I'm glad to have heard you put XY on the level of black magic. That's part of my work, my own work from some years back. And
yeah,
I'm
calling it. Yeah, I call it black magic because, as far as I know, XY doesn't use PGF in the backend, right?
And there is a backend which can do some of that, but yeah, it needs to be redeveloped. And Diane's been putting some work into it too. So
nice.
So there could be things happening there. Anyway, okay. So some more questions in the Q&A. Yeah, okay. So David Carlisle's put a link in the Q&A, and others are just saying thanks.